Okay, here's part two. I'm going to give you just some of the answers so I can do a couple in depth. So number three, here's velocity when it hits the ground. You find when it hits the ground, you plug it in. Here's one comparing a ball dropped at 100 feet and a ball dropped at 75 feet. I compare their times, and I added 1 second to here because it gets to fall for a second more since you dropped it earlier. Yeah, so you can pause that, take a look at them because I want to spend a little more time on the other page. Don't do number 4. Don't worry about it. It's too crazy. Let's do number 5, and you can kind of see what goes on with it. A projectile shot upward with a initial velocity of 384 feet per second. So you always have the negative 16 t squared. That's because of gravity. If you shoot something upward, you would give a positive 384 t. Because you're basically using this equation, the h of t equals, this is your gravity, and your initial velocity times t, and your initial height. So it's h sub 0. So basically that's always there. This is positive if you shoot up. It's negative if you throw something down, which the one thing I did like about this problem was it had you throwing something downward. There's your equation, and it just asks what's the velocity after 5 seconds and after 10 seconds. So if I have this and I want to get to velocity, all I do is take the derivative, right? I use my derivative rules. Luckily, we don't have to do this with the long way. I'm going to do v of 5 right, which is 224 feet per second. You want to put your units on there, and then v of 10 is going to be negative 32 times 10 plus 384, which is 64 feet per second, which sounds weird at first. Like, holy cow, why is that slowing down? Well, you're shooting it upward. So it starts off fast, but gravity's trying to slow it down, and then it goes to the very top, and then comes back down and gets faster and faster. So it makes sense that it's actually slowing down. This one's like repeat your steps here after 1 second and 5 seconds, or 5 seconds and 10 seconds. And what happens here? So I imagine we have our same projectile being shot upward. So we got gravity. We shoot upward at 256 feet per second. Our velocity equation would now be negative 32 t plus 256. Doesn't look much different. For the first part, at 5 seconds in, so I shoot this thing upward, 5 seconds in, you're going to have negative 32 times 5 plus 256. That's going to equal 96 feet per second. Not surprising that's lower because I shot it at a slower speed, right? Here's where it gets a little interesting, is if you look 10 seconds in and I shot at a lower speed, I bet it doesn't go as high. And you plug in a 10, and you'll get negative 64 feet per second. Like, how can you have negative 64? That means it went up, right? Your projectile went up, 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 up. So it's super fast early on, right? Then it gets slower and slower. Eventually it gets to the very top. It stops for an instant in time, not long enough to see it like Wile E. Coyote. Then it starts falling back down and gets a negative velocity. It's like this is a negative velocity by the time you're coming down, and then it gets faster and faster and faster going downward. So it's kind of crazy. All right, so let's jump over here real quick. To estimate the height of a building, a stone is dropped from the top into a pool of water at ground level. You could actually do this. How high is the building if the splash is 6.8 seconds after the stone is dropped? So this is a little weird question because you're used to writing your formula. You have gravity, negative 16 t squared. You don't have a initial velocity if you drop something, anytime you see dropped, you're basically saying my starting velocity is 0. So it makes that VOT go away. The question is, how high is it originally? So I'm going to first write this without knowing. I'm just going to put an h of 0. That's my initial height, right? It's my starting height. So here, I want to know what the starting height is, which means I probably have more info I haven't used here. You're like, wait a second. At 6.8 seconds, so I can type in a 6.8 here. What happens at 6.8 seconds? Well, at 6.8 seconds, it splashes, also known as height equals 0 at that time. So at 6.8 seconds, my height is 0, and I can use this to solve for h sub o, because I can move that to the other side, square it, you get 739.8 feet. And that would be your estimate. So you could actually estimate how tall a building is by dropping something off, which is never a good idea because there could be people down below. One last weird question, but you do this in physics class a lot, and that is the graphs of position functions are given. So this is a graph of a position. Imagine something, you can track how far it's gone in miles and how long it's taken. You know, your phone can probably track that. And I want to make a graph of the velocity in miles per minute over time in minutes. I want to change it from a distance graph to a velocity graph. And it's kind of weird, but I want to make the time match. I'm going to have 2, 4, 6, 8, 10. I can actually get a really accurate graph here because if I look from here to here, it kind of behaves the same way the whole time. From 0 minutes to 4 minutes. How far did it travel from 0 to 4 minutes? How far did it go? We went 2 miles, right? So if I go 2 miles in 4 minutes, that's an average of a half mile per minute. So that's my rate. That's a rate right there. You just took a distance and a time and divided them, and you can get a rate out of it. Well, guess what? If I make this 0.5 and this 1, it's a constant rate. See how that's an angle the whole time? Its slope is the same. That's what I wanted you to get out of this is, if you think about it, derivatives find the slope of a graph at any point. Well, it has a constant slope. Guess what the slope is? 1/2, or up 1, right 2. It's a rise over run. So you go with a constant slope of half a mile a minute, and then it looks like you stop all of a sudden because your distance doesn't go forward anymore. So from 4 to 6 minutes, you've traveled no distance, which is 0 miles per minute. Well, that's easy to graph, but what's weird is it like drops straight down. I don't know how you went from moving that fast to 0 that quickly, unless you like hit a brick wall, but ouch. And then all of a sudden you must have a good acceleration here because look at this slope. Doesn't this slope look steeper than that slope? Well, you can figure it out. Look at those numbers. From 6 to 10 minutes, I traveled a total of, it went from 2 to 6 miles. So I went 4 miles from 6 to 10 minutes here. I went 4 miles in 4 minutes, which is 1 mile per minute. So I'm going to go up here, and for that whole time from 6 to 8 or 6 to 10, I'm going at 1 mile per minute. So that's 60 miles per hour. And it jumps. This is a little unreasonable to think you jump like that. But what's kind of cool is you can start to hopefully see, like, oh my gosh, if I just thought of the slope here, which is 1/2, from here to here the slope is 1/2, but it's weird because it's constant. If I just thought about the slope, I have a constant slope. I have a zero slope, and I have a constant slope that's more steep, so it's a higher number, but it's still constant. And if I had a graph that went back down, I would have a negative slope like down here, which would be weird, you know. So anyway, just something to think about. It's weird that you can make relationships between the graphs of the velocity and the distance. Anyway, hopefully that works for you. And yeah, soak it in, and then you're going to do another problem set kind of on your own that you're going to turn in on part B. All right, talk to you later.